In this video, we work our second example involving Simpson's rule. We're asked to approximate the integral below using Simpson's rule with an error less than 0.0000 or 0.0001. And so we want the integral from a to b of the square root of 1 plus x squared. With the techniques we've learned in Calculus 1, we can't evaluate that integral. We'll actually learn a technique at the beginning of Calculus 2 called trigonometric substitution that will allow us to evaluate that. But for now, we'll use Simpson's rule, which will be in which we'll be approximating this function on a number of subintervals with a second-degree polynomial. Now we're told that when we use Simpson's rule, this is from the text, that the error is less than or equal to b minus a to the fifth divided by 180 times n to the fourth, where n is the number of subintervals, times the maximum value of the fourth derivative of, or the absolute value of the fourth derivative of the function on our interval. Now, as long as that function is continuous on the interval from a to b, by the extreme value theorem, it definitely has a max. So we can find that maximum. We can multiply it by this b minus a to the fifth. B is 1, a is 0 in this case, so that's just 1 to the fifth. And then we'll have an expression here involving n. If we want to use Simpson's rule with an error less than 0.001, what we need to do is choose n so that this maximum possible error is less than that 0.001. So let's do that. In order to do that, we need to compute the fourth derivative of this function, and then maybe we can graph it and also look at its absolute value. The original function is that 1 plus x squared to the 1/2 power, because we can always write that square root as a 1/2 power. And if we write it like that, it's easier to see that we'll have to use the chain rule. We've got an inside function and an outside function. So my inside function is that 1 plus x squared. It's inside that square root function. The derivative of a function raised to the 1/2 power is 1/2 of the function raised to the 1 less power. 1/2 minus 1 is negative 1/2. We put the function back inside, and then we multiply by the derivative of the inside by the chain rule. In this case, that's 2x. Now, if we simplify, we've got the 1/2 times the 2 is just a 1. This x will remain in the numerator, and that expression to the negative 1/2 can be placed in the denominator. That's the same as having a 1 plus x squared to the positive 1/2 in the denominator. So that's our first derivative. Now for our second derivative, we'll have to use the quotient rule. So I'll use our little mnemonic. If we call this the high function and this the low function, the mnemonic for the derivative of a quotient is low d high minus high d low over low low. And that d is an operator, it applies to what's in front of it. So that tells us that what the derivative of this quotient is low, so the bottom function. D high, it's the derivative of the top function, so 1 in this case, minus high, which is x, times d low, that's the derivative with respect to x, of that 1 plus x squared to the 1/2 again, all divided by low low. The square root of something times the square root of something is just whatever was under the radical, provided that thing is positive, and 1 plus x squared is always positive. So we've got that. And then again, the derivative of this requires the chain rule. We did that earlier. This derivative is this x divided by 1 plus x squared to the 1/2. If we applied the chain rule again, that's what we would get. Now I've got a fraction within a fraction. To clear that fraction within a fraction, I'll multiply the numerator and denominator by 1 plus x squared to the 1/2. And then we'll distribute that this times this is our first term, and then we'll have this expression times that is our second term. Square root times itself is just going to give us a 1 plus x squared. And then the square root in the numerator and the square root in the denominator here, when we multiply those will cancel. We'll just have a negative x squared. And then I've got an x squared plus 1 to the first times an x squared plus 1 to the 1/2. So we add the exponents. That's 1.5 or 3/2 as our new exponent. And the x squared and the negative x squared reduce. So this ends up being x squared plus 1 to the negative 3/2. Okay, that's nice. Not too bad. And we need a fourth derivative, so we have to keep going. Take the derivative again. We'll use the chain rule again. Here's our inside function. We bring the power down. We multiply by the original function to the 1 less power. Negative 3/2 minus 1 is negative 5/2. It's the derivative of the outside, evaluated at the inside. So you put your inside function back inside and then multiply by the derivative of the inside by the chain rule. This 2 and that 2 reduce, and we end up with a negative 3x in the numerator. And this with the negative exponent can be placed in the denominator. That's x squared plus 1 to the positive 5/2 in the denominator. So that's our fourth derivative, or third derivative, sorry. We need the fourth derivative. Since I've got a function of x in the numerator, I'll use the quotient rule again. The derivative of high over low is low d high, and the derivative of the negative 3x is just negative 3 minus high. So we're subtracting negative 3x, it gives us positive 3x. D low. Now this requires the chain rule. Got my inside function again, raised to the 5/2. So if I have a function raised to the 5/2, we'll get 5/2 times that original function to the 1 less power. 5/2 minus 1 is 3/2. Put the inside function back inside and multiply by the derivative of the inside by the chain rule. Divide all of that by x squared plus 5 to the 5/2 squared. If you multiply those exponents, you're just going to get an x squared plus 1 to the 5th. The 2's reduce there. And we notice that we've got an x squared plus 1 to the 5/2 here and an x squared plus 1 to the 3/2 there. We can factor out an x squared plus 1 to the 3/2. And then we say x squared plus 1 to the 3/2 times what will give us this? Well, I need another x squared plus 1 to the first, because 3/2 plus 1 would give us that 5/2 times the negative 3. And then we've factored that out. And we're left with a 3x times a 5x. So that's 15x squared. And then we still have that x squared plus 1 to the 5th in the denominator. And that will reduce with this. 5 is the same as 10/2. So if I subtract those, I'll get a negative 7/2. So I'll put it next to the, or x squared plus 1 to the 7/2 in the denominator. If I distribute that negative 3 in the numerator, this is what I get. 15x squared minus 3x squared is 12x squared. All right, so this is our function. We could just graph this on Desmos.com and look for the maximum. Or we could take the fifth derivative, set the fifth derivative equal to 0, and think about when the fifth derivative changes signs. Then we would know when this function is increasing versus when it's decreasing, and we could find a maximum that way. Like, we're in Calculus 1, let's take a derivative. It's a good review at the end of the semester. So we'll take the derivative with respect to x of the quotient again. So low d high. The derivative of the top function is 24x minus high below requires the chain rule. So we've got a function raised to the 7/2 power. So we get 7/2 of the function to the 5/2. Put the inside function back inside, multiply by the derivative of the inside by the chain rule. All divided by low. So we have x squared plus 1 to the 7/2 squared. That's just going to be x squared plus 1 to the 7th. All right. Almost done. If I try to simplify my numerator, those 2's reduce, and I notice I've got an x squared plus 1 to the 5/2 and an x squared plus 1 to the 7/2. So I'll factor out that x squared plus 1 to the 5/2 from the numerator. Then x squared plus 1 to the 5/2 times an extra x squared plus 1 gives me that first expression. Then we have to multiply by the 24x as well. Then we're subtracting 12x squared minus 3 times 7x, and this we've already factored out. All of that is divided by x squared plus 1 to the 7th. Or if you want, you can call that 14/2. And then 5/2 minus 14/2 is going to give us a negative 9/2. So we'll put an x to the x squared plus 1 to the 9/2 in the denominator. And then we can distribute in the numerator. So we're going to have 24x cubed plus 24x. And then we have to distribute the 7x there as well. And there's not, well, actually there is enough space. If we distribute that 7x to the 12x squared, we get, what's that, 70 plus 14, 84x cubed. And then we have a negative 21x times the negative 1 is positive 21x. And so we can collect like terms. The negative 24x cubed minus 84x cubed is negative 60x cubed. And that 24x plus 21x is 45x. And we're dividing everything by x squared plus 1 to the 9/2. And we want to set this equal to 0 and figure out where it changes signs to find the maximum of the fourth derivative. So we'll factor this as much as possible. In the numerator, we see we've got a factor of 15x in common here. We can factor out from both of those things, the greatest common factor. 15x times 3 would give me that 45x. 15x times negative 4x squared would give me the second, or this other term. That covers both of those. We'd say, okay, well, where does this change signs? Well, the fifth derivative is equal to 0 when the numerator is 0. So that's when 15x is 0, or when 3 minus 4x squared is 0. So if we solve this one for x, we get x equals 0. We solve this one for x, we get 4x squared has to be 3, so x squared must be 3/4. So x must be plus or minus the square root of 3 over 2. Now remember, we were talking about Simpson's rule for a particular function here. So we're only interested in the interval from 0 to 1. Our fifth derivative is 0 at 0, and it's also equal to 0 at the positive square root of 3 over 2. That's on our interval, but the negative square root of 3 over 2 is not on our interval. So we're really just interested in what happens at x equals negative, or at positive square root of 3 over 2. So we're on the interval from 0 to 1. That's where the fifth derivative might potentially change signs. Now the fifth derivative is this 15x times 3 minus 4x squared divided by x squared plus 1 raised to the 9/2. X is positive on both of these intervals, so 15x will be positive, so will the x squared plus 1 to the 9/2. The only thing that might change signs is this 3 minus 4x squared. And it's easy to see what the sign should be if you graph that. That's just an upside down parabola. It crosses the x-axis at x equals plus or minus square root of 3 over 2. So it's the function is positive to between 0 and the positive square root of 3 over 2, and then it's negative after the square root of 3 over 2. So we have a positive here and a negative here, so it's positive there and a negative there. So the original function, that's the fourth derivative, goes from increasing to having a zero slope to decreasing at this value. So our fourth derivative must have a maximum at that value. So this value should be the relative maximum of, or a relative maximum of that function. And the fourth derivative, we calculated that. It was this 12x squared minus 3 divided by that expression. I think that was to the 7 halves, wasn't it? So it's super simple, just a lot of calculations. Square the numerator and square the denominator. You're going to get 3 divided by 4. 4 goes into 12 3 times. So I have 3/4 plus 1 down here. So you can call that a 4/4 if you want to. So I've got 9 minus 3 in the numerator, which is 6, divided by 7/4 to the 7 halves power. I'm just going to write that as 6 times 7/4 to the negative 7 halves power. I'm not going to worry about simplifying it. I'll find out what that is. And that should be the maximum value of our function on the interval of interest. All right, let's actually graph that and make sure that that's true. Confirm that our fourth derivative actually has a maximum there by looking at the graph on Desmos. Okay, so this is our fourth derivative. It looks like it does have a relative maximum at x equals square root of 3/2. I just evaluated it at square root of 3/2 and I plotted the point, and then I typed in my exact answer, and I see that my exact answer is the same as the answer that is given by Desmos when I evaluate the function there. So it looks like I've done this correctly, provided I differentiated correctly. So that is our maximum. That's 6 times 7 divided by 4 to the negative 7 halves, which is approximately 0.846. Just writing that down. Okay, so now we can substitute that into our error formula for Simpson's rule. So let's go back to this. So this is the original function, f of x equals the square root of 1 plus x squared. That's the area that we're trying to approximate. We can compute the definite integral using Desmos. They're saying that it's approximately this 1.1478 number. And also compute it using trigonometric substitution. We'll learn that in calculus 2. This is the exact answer. When we look at the decimal approximation of that, we see that it matches the answer given by Desmos. We say, okay, we want to use Simpson's rule to approximate this function though. Because we're in calculus 1 and we don't actually have those techniques from calculus 2 yet. And we don't just want to rely on a black box, graphing calculator to do the calculations for us. Like we want to actually know sort of where the numerical methods come from, and that's why we're studying Simpson's rule. So we've got the numerical method, we're familiar with its background, but we know that every time we use a numerical method, there's some error. So we're told that this is the maximum error, and we just maximize that fourth derivative on the interval of interest. Actually, let me look back at that other graph. That is the maximum value of the function, but look at it. I didn't take the absolute value, did I? I totally didn't even think of that. Let's see. There's the fourth derivative. And what I need to graph is the absolute value of the fourth derivative. On the interval of interest, the maximum occurs at x equals 0. The maximum value is 3. So we did all that calculation and we didn't need to. Whenever we do use the extreme value theorem from at the beginning of the course, we say, if this function is continuous on the closed interval from a to b, any extrema will occur either at the endpoints or on the interior of the interval. We found an interior point that was a potential relative extrema, but we didn't look at the absolute value and we didn't look at the endpoints. But the graph suggested, maybe we should look at the absolute value. So this is when we're grateful that we use graphing calculators, right? Because when we look at the absolute value, that's taking all of these negative values and flipping them up so that they're above the y-axis now. We see that when we take the absolute value, the maximum occurs at x equals 0. And again, we're just interested in this interval from 0 to 1. It's a little bit difficult to see with the grid. But let's see, maybe I should just do that for x between 0 and 1. We're just interested in that part. Well, then the maximum is clearly 3. All right, so now we're going to use the correct value. So Simpson's rule. So the maximum error is given by this formula. And so it's the maximum error is given by b minus a raised to the 5th divided by 180 n to the 4th times the maximum value of the function, of the absolute value of the function, the 4th derivative of the function on the interval of interest. And I think I want to do that calculation on paper. Okay, so the interval of interest was the interval from 0 to 1, because this was our integral. So b is 1, a is 0, so we just have 1 minus 0 to the 5th divided by 180 times n to the 4th times the maximum value of that the absolute value of the 4th derivative, which is 3. So we get 3 goes into 180 60 times, so we end up with 1 divided by 60 times n to the 4th. And in the problem statement, I think we said, where did it go? We want our error to be less than 0.0001. And this is the maximum error. So we want this quantity to be less than 0.0001. So we'll multiply both sides by that 60 times n to the 4th. And we'll divide both sides by the 60 times that number. And then we want to take the 4th root of both sides.
Large.
This is going to give us a lower bound for our n. And I'll use the graphing calculator to compute that. So when we calculate that, we see our n has to be greater than that 3.593. And of course, n has to be an integer. And when we use Simpson's rule, it has to be an even integer. So we're saying n has to be greater than or equal to 4 in order to get our error less than that 0.0001 quantity. So we're going to use n equals 4 again. All right, so that's the plan. And let's type that in our Desmos graph. We'll say the error will be less than the 0.001 when n is greater than or equal to 4. So we'll use 4 subintervals, just like we did last time. Okay, so this is our function. F of x equals the square root of 1 plus x squared. We're on the interval from 0 to 1. So we subdivide that into 4 subintervals of equal width. So they're each going to have a length of 1/4. So our first endpoint is at x equals 0. We evaluate the function. Then we evaluate at 1/4, then 1/2, then 3/4, and then 1. And then we'll just do the calculations. 0 squared is 0. We're taking the square root of 1, which is 1 there. And here I've got 1 plus 1/4 squared, so that's 1 plus 1/16. I can call that 1/16 divided by 16. And so I've got a square root of 17 divided by 16. Square root of 17, I can't simplify. I'll just write that as square root of 17 divided by square root of 16, which is 4. If I square the 1/2, I get 1/4. Then I'll write the 1 as 4 over 4, so I can combine them. Then I'll have 5 divided by 4 under the radical. So when we take the square root, we'll have the square root of 5 divided by the square root of 4, which is 2. Here, we'll square the numerator and the denominator, so we'll have 9 16ths there. So then we'll have 16 divided by 16 plus 9 divided by 16 under the radical, just so that we can get that common denominator. And we'll have 25 divided by 16, take the square root of the numerator and denominator, you'll have 5/4. And 1 squared is 1, 1 plus 1 is 2, so this is the square root of 2. And I believe that's approximately 1.4-ish. So my graph is going to look like this. And these are our function values. They're given by these, and we can approximate the function with a second degree polynomial using this x value, or x equals 0, x equals 1/4, and x equals 1/2. And then we'll approximate the function using a polynomial with x equals 1/2, x equals 3/4, and x equals 1. If we do that, then this is the approximate area under the curve, or the value that we get using Simpson's rules, approximate area under the curve using those two polynomials. And Simpson's rule says that that value is b minus a divided by 3 times n, where n is the number of subintervals. We evaluate at a, and then we add 4 times that function value at a plus delta x, which we usually call x sub 1. And then we have 2 times f at x sub 2, and then 4 times f at x sub 3. And then since there are only 4 subintervals for us, we'll just have the last value, that's f at x sub 4. And in our case, b and a are 1, and n is 4. So we're going to have 1 minus 0 divided by 3 times 4, which is going to give us a 1/12 out front. And then we'll have f at 0 plus 4 times f at 1 plus 2 times f at 2 plus 4 times f at, I'm saying 1, sorry, this is 1/4. It should be 2/4 or 1/2, 3/4, and then f at 1. That's what we want. Okay, I'm thinking x sub 1, x sub 2. And we already found these function values. F at 1 was 1. And then we're adding 4 times the function value at 1/4, which was square root of 17 divided by 4. So the 4's reduce. And then we've got 2 times f at 1/2, which was square root of 5 over 2. The 2's reduce. Then we'll add 4 times f evaluated at 3/4, which gives us that, f at 3/4 is 5/4, so the 4's reduce. And then f at 1 is square root of 2. So that area under the curve is approximately I've got a 1 and a 5, that's a 6, plus square root of 17, plus square root of 5, plus square root of 2, all divided by 12. And we can use Desmos to see what that number is. Now remember where this comes from? We had this coefficient, and then we had the area under the curve for each polynomial was on that interval from 0 to 1/2. It's going to be this b minus a divided by 3n times f at 0 plus 4 times f at 1 plus 1 times f at 1/2, or f at 1/4 plus 1 times f at 1/2. But then we use that value again for the second polynomial, which is why we got that 2 in the middle. So that's our Approximation using Simpson's rule. Let's check on Desmos. So the approximation that I got doing the hand calculations and the approximation that Desmos got just using the formulas and the substitution of b equals 1, a equals 0, and n equals 4. Those are the same. So we know that our approximation is good. If we look at the difference between the true value of the integral and our approximation, we see it's 0.00001, which is less than that 0.0001 that we wanted. So that's good. We're within our maximum error, which is a very good thing. You might say, okay, well, how can we actually look at that graph? I want to see the polynomials. Well, we can do that. Desmos can sort of do the calculations for us, solving those systems of 3 equations and 3 unknowns to get those polynomials on each interval. If we want to do that, we can just plot some points. We'll type our first 3 x values, 0, 1/4, and 1/2, or 0.25 and 0.5. And then we'll evaluate the functions there. So that gives us those first 3 points. Actually, oops, I didn't mean to do that. I plotted these earlier after we said n equals 4. I'm going to get rid of those now, just so that we can emphasize what we're plotting with these tables. So we plot our ordered pairs for x equals 0, 1/4, and 1/2 using the function, adding or evaluating the function at those values. We get these values. And we can ask Desmos to calculate that second degree polynomial for us. If we do that, we just use this tilde. We're using the regression capabilities of Desmos. It gives us the coefficients a, b, and c. So my first polynomial looks like this. You can't even see the difference between that function and the approximation. They're so close to each other. And then the area that we're using to approximate the area under the curve is that area. Looks pretty good to me. Then we're interested in the function at 1/2, at 3/4, and at 1. So we'll plot those points. And then we will use Desmos to give us a polynomial here. I'm using x sub 2 here, and I used x sub 1 on the first one, so that that Desmos is only using those 3 values of x. And it'll give us the correct coefficients a, b, and c for our quadratic polynomial. Then I just type that in. I'm using the same notation that I used here, so that a sub 2, b sub 2, and c sub 2 are the values computed by the regression calculator on Desmos. So we see when we graph that, it's almost indistinguishable from the original curve. And then that's the area of the region that we're interested in. And again, when we look at the difference between the actual area under the curve and our approximation, it's 0.00001. Very, very small. So we know we're doing this correctly. And we also know how to get our error to be as small as we want by choosing n large enough. The hard part of that is that you have to calculate that 4th derivative, look at its absolute value, and find the maximum on the interval of interest. But you can always do that because of the extreme value theorem. So you'll just take this inequality once you do that, set it less than the desired error, and then just solve for n. And we said, okay, if n has to be greater than this 3.59, we'll let n equal 4, and that works. It gives us a very good approximation of the integral. But we can find an exact value of that integral. We will find an exact value of that integral in Calculus 2. When we learn advanced integration techniques, we'll learn integration by parts, we'll learn a lot of really cool techniques. We can find the exact answers and you don't have to approximate anything. But that's it. That's the end of Calculus 1. Hope you enjoyed the course. Let me know if you have any questions.